Is our entire picture of reality fundamentally incomplete? A radical new idea in physics suggests it might be. The theory of causal fermion systems proposes a complete rewrite of our cosmic rulebook, a new foundation for all of physics. This single framework aims to achieve the Holy Grail, unifying the laws of the very small quantum field theory with the laws of gravity and the cosmos' general relativity. By the end of this exploration, you will understand how this theory could redefine the very nature of space, time, and matter itself. We will uncover how our smooth, continuous universe might emerge from something far more discrete, and what this means for the ultimate fate of our cosmos. What does it truly mean for reality to be built from something more fundamental? The universe might not be built from tiny dots floating in an empty container. The theory of causal fermion systems suggests a far more interconnected reality. At its heart, this theory proposes that the fundamental ingredient of everything is a single, precise mathematical object called a causal fermion system. Forget the idea of separate particles and the stage they move on. In this picture, matter and the fabric of space-time are not just interacting partners, they are fused together, born from the same underlying structure. This mathematical object encodes all of physical reality at once, the particles and the arena they exist within, making them two sides of the same cosmic coin from the very beginning. This is a radical departure from our current theories, which treat particles as one thing and the gravitational field of space-time as another, then struggle to make them get along. Here, there is no separation to begin with. The stage and the actors emerge together from a deeper, more fundamental script. This beautiful fusion of matter and space-time is a solution to the deepest crisis in modern physics. For over a century, two magnificent but incompatible theories have described our universe. Quantum field theory gives us the rules for the subatomic world, a bizarre and probabilistic realm where particles can be in multiple places at once. General relativity, meanwhile, masterfully describes gravity and the cosmos, picturing space-time as a smooth, curving fabric. The problem is, these two rulebooks are written in different languages. They fundamentally disagree when applied to the same extreme situations. Think of a black hole's center or the very first moment of the Big Bang. Our current math hits a wall, predicting a point of infinite density and temperature, a singularity where the laws of physics simply break down. This is a clear signal that our understanding is incomplete. We have been trying to glue these two theories together for decades. One famous attempt, string theory, proposes that everything is made of tiny, vibrating strings. While mathematically elegant, it has so far struggled to make concrete predictions that we can test in experiments. Without experimental proof, a theory remains a beautiful idea trapped in the abstract. The crisis remains. We are missing the foundational principle that seamlessly weaves the quantum world with the gravitational cosmos, a single origin story for all of reality. This crisis demands we question not just our theories, but our deepest assumptions about reality itself. For centuries, physics has been built upon the idea of a smooth, continuous universe. We picture space and time as an unbroken fabric, a flowing river where any point can be divided infinitely, forever. This is the continuum, the very stage upon which our cosmic dramas play out. But what if this stage is not fundamental? The theory of causal fermion systems proposes a truly radical shift. It suggests that the smooth, continuous space-time we experience is not the bedrock of reality. Instead, it emerges from something far more basic, a sea of discrete, fundamental building blocks. The continuum is an illusion, a beautiful and convincing approximation, much like a digital photograph. When you look at a high-resolution image on a screen, you see a smooth, continuous picture. You see a face, a landscape, a gradient of color, but zoom in far enough and this illusion shatters. You find the pixels, the tiny, indivisible dots of color that have no image in and of themselves. Only when you step back do these discrete bits assemble into the seamless whole we perceive. The theory posits that space-time itself is that image, and the causal Fermion system is the pixel grid. There is no smooth fabric at the most fundamental level. There are only these discrete mathematical events, these fundamental relations, and from their intricate patterns, the familiar concepts of location, duration, and even causality themselves crystallize into existence. This transforms our understanding of the universe from a continuous stage to a cosmic computation, a vast network of information being processed. What does this mean for the fabric of reality? It suggests that at the very smallest scales, the universe is granular. There is a fundamental limit to how finely we can divide space and time, a smallest possible unit. This resolves the mathematical nightmares of infinities that plague our current theories, because you cannot cram infinite energy into an infinitely small point if there are no infinitely small points. The void of empty space is not empty at all, but teeming with this fundamental, discrete structure. So, the next time you gaze at the seamless night sky, remember you might be looking at the most magnificent illusion of all, a masterpiece painted with discrete, invisible brushstrokes. So what exactly is this fundamental building block, this fermion, that gives the theory its name? To understand its power, we first need to look at the universe of particles. All the matter you see around you, from the screen you are watching this on to the very atoms in your body, is made of a class of particles called fermions. Think of electrons swirling around the nucleus of an atom, or the quarks that bind together to form protons and neutrons. These are all fermions. They are the ultimate individualists of the particle world, governed by a profound rule known as the Pauli exclusion principle. This principle is the cosmic law that prevents them from being in the exact same place, doing the exact same thing at the same time. It is the reason electrons occupy different shells around an atom, the reason you cannot push your hand through a solid desk, the reason matter has structure and volume and does not simply collapse into a formless, dense blob. Without this rule, atoms could not form, chemistry would not exist, and the complex universe we know would be impossible. This is the critical distinction between fermions and their cousin particles, bosons. Bosons, like photons of light, are the social butterflies. They love to congregate, to pile into the same quantum state, which is what makes phenomena like lasers possible. But for building a stable, structured reality, you need the stubborn, individualistic nature of fermions. They are the bricks of the universe, not the mortar. This is precisely why the theory of causal Fermion systems chooses them as its fundamental entity. It is building reality from the ground up with the only particles that inherently enforce structure and avoid collapse. In this framework, the fermion is not just a tiny ball bouncing around in space. It is a more abstract mathematical object, a package of information that encodes both its own properties and the very nature of the space-time point it defines. The Pauli exclusion principle is then not just a rule they follow, but a fundamental feature woven into the fabric of this new reality from the very beginning, ensuring that the emergent universe has structure, depth, and a stable foundation. This stubborn individuality of fermions is only half the story, because the theory's name points to something even more profound: causality. The word causal is not just a label, it is the very bedrock upon which this entire framework is constructed. In the universe we experience, cause always comes before effect. A pebble hits the water before the ripples spread. A decision is made before an action is taken. This fundamental principle of cause and effect is the thread that weaves the fabric of our reality, creating a coherent sequence of events from the chaos of the microscopic world. The theory of causal Fermion systems takes this intuitive concept and elevates it to a foundational law, hardwiring it directly into its mathematical core. The structure of the entire system is defined by a web of cause and effect relations between its fundamental events. This is a radical shift in thinking. In many other approaches to unifying physics, causality is something that emerges later, a property that hopefully falls out of the complex equations. Here it is the starting point. The universe is not built first and then taught the rules of cause and effect. It is constructed from them. This single, powerful constraint resolves some of the most baffling paradoxes that appear when we try to merge gravity with quantum mechanics. Consider the infamous problem of time travel paradoxes, where an effect could loop back to become its own cause, creating logical impossibilities. In a universe built on a causal Fermion system, such paradoxes are mathematically forbidden from the outset. The architecture of reality itself ensures that the arrow of time has a single, consistent direction. Every fundamental event, every point in this discrete space-time knows its place in the causal order. One event can only influence another if it is in its past, creating a cosmic tapestry where every thread is connected in a way that respects the unbreakable chain of cause and effect. This provides a stunningly elegant solution to problems that have troubled physicists for generations, not by adding complex new rules, but by building the most basic rule of our experience directly into the heart of reality. This causal architecture is brought to life by a precise mathematical engine. Think of a causal Fermion system as a vast dynamic network. Each point in this network is not a location in space, but a complex mathematical object called an operator, acting on what physicists call a Hilbert space. Now, a Hilbert space might sound intimidating, but you can picture it as the universe's ultimate stage for all possible quantum states. It is the abstract arena where the probabilities and possibilities of quantum mechanics play out. In our cosmic network, each operator is a single node, and it does not just sit there. It actively shapes a tiny piece of this quantum stage, defining what can and cannot happen at that point. The magic, the thing that makes this a causal Fermion system, is in the connections between these nodes. They are not all connected. The web is woven with strict, unbreakable causal rules. One node can only influence another if it is in its direct causal past. This creates a cosmic flow of information, a ripple of cause and effect that propagates through the entire network, forbidding any paradoxical loops. The smooth, four-dimensional space-time we experience is the emergent picture we get when we step back from this intricate, buzzing network of discrete causal relations. It is the forest we see after understanding every single tree and the precise pathways that connect them. This elegant mathematical network gives rise to the most fundamental illusion of all, the very stage of our reality. The four-dimensional space-time we inhabit, with its 3 dimensions of space and 1 of time, is not a primary ingredient of the universe. It is a collective behavior, a pattern that crystallizes from the endless, dynamic interactions within the causal Fermion system. Think of the air in a room. It has a property we call temperature. You can feel it, measure it, and it has real effects on everything around you. But if you could zoom in to the atomic level, you would find a chaotic dance of individual molecules, each with its own speed and energy. You would search in vain for a single molecule that has temperature. Temperature does not exist at that fundamental scale. It is an emergent property, a statistical average that only makes sense when you consider the trillions upon trillions of molecules moving together. The smooth, continuous space-time of our daily experience is exactly like that temperature. It is not a fundamental field or a container. It is what physicists call an emergent phenomenon. It is the collective story told by the countless discrete events in the underlying causal Fermion system. Each of these fundamental events is like a single molecule in our analogy. It has its own complex internal structure, but it knows nothing of length, width, or duration. These concepts are meaningless at that most basic level. Yet, when you have an immense number of these events, and they interact with each other according to strict causal rules, a magnificent pattern emerges. The correlations between these events, the way they link and influence one another, create a web of relationships that our brains and our instruments interpret as proximity, as distance, as the orderly flow of time. A short causal distance in the underlying network translates to being close together in emergent space. A long causal chain translates to being far apart. The direction of these causal links defines the arrow of time itself. So when you reach out to touch something, you are not moving your hand through a pre-existing space. You are, at the most fundamental level, initiating a vast, complex cascade of interactions within the causal fermion system, a cascade whose overall pattern we have learned to describe as motion through a three-dimensional world. This is perhaps the most profound insight this theory offers. The stage of the universe is not set before the play begins. The actors, through their intricate performance, build the stage itself with every passing moment. This very fusion of actor and stage holds the key to one of physics' greatest mysteries. For decades, the central challenge has been that our two most successful theories, quantum mechanics and general relativity, describe reality in languages that seem mutually exclusive. One deals in probabilities and discrete jumps, the other in a smooth, deterministic fabric. The theory of causal fermion systems speaks a single, unified language from the very beginning. Because the fundamental object describes both matter and the arena it exists in simultaneously, the problem of unification simply evaporates. There is nothing to unify because they were never truly separate. In this picture, gravity is not a force that needs to be quantized or added to the quantum world. It is not a separate actor on the stage. Instead, gravity emerges as an inherent property, a direct consequence of the complex interactions within the causal fermion system. It is the natural shape of the emergent space-time fabric, a shape that is dynamically woven by the presence and behavior of the matter it contains. Think of a vast, interconnected network of springs. Each connection represents a causal link in the fundamental structure. When you place a heavy weight on one part of this network, it deforms. It stretches some springs and compresses others, changing the entire geometry of the web around it. In this analogy, the heavy weight is a massive object like a star, and the resulting deformation of the network is what we experience as gravity. The star is not pulling on other objects with a mysterious force. It is simply reshaping the very stage upon which everything else exists, and other objects follow the contours of this reshaped stage. This is a breathtakingly elegant solution. It sidesteps the mathematical nightmares that occur when you try to force gravity into the probabilistic framework of quantum field theory. In those attempts, calculations often produce nonsensical infinities, a clear sign that the approach is flawed. But in the causal fermion framework, the discrete, fundamental nature of the underlying structure prevents these infinities from ever appearing. There is no infinitely small point for energy to concentrate into because the fundamental building blocks provide a natural, minimal scale. This means the theory can, in principle, describe the most extreme environments in the universe without breaking down. It can peer into the heart of a black hole or rewind the clock to the first instant of the Big Bang, not as points of infinite mystery, but as regions of incredibly dense yet finite interaction within the causal web. The unification of quantum theory and gravity is not a forced marriage in this view, but the recognition of a deeper, singular origin. They were always two different descriptions of the same underlying causal reality. This unified picture of reality must prove its worth by predicting the world we see. What concrete phenomena can this theory actually forecast? Its most profound predictions lie at the very edge of our understanding, in realms where our current laws of physics fail. One such frontier is the Planck scale, the smallest possible size in the universe, a distance so minuscule that it is a trillion times smaller than an atom. At this unimaginable scale, our classical idea of smooth space and time shatters completely. The theory of causal fermion systems predicts that here, the very concepts of here and there lose their meaning. Space-time becomes a seething, dynamic foam, a probabilistic dance of the fundamental causal events. It is not a chaotic mess, but a structured chaos governed by the strict causal rules of the underlying network. This is not empty speculation. It is a direct mathematical consequence of replacing the continuum with a discrete structure. This foamy nature of space-time at the Planck scale could leave faint imprints on the light traveling to us from the most distant corners of the cosmos, a subtle flicker that future telescopes might one day detect, offering us our first glimpse into the fundamental grain of reality. Another arena for prediction is the heart of a black hole. Our current theories point to a singularity, a point of infinite density where all known laws break down. But infinities are a sign of a theory's limits, not a description of nature. The causal fermion framework, with its discrete building blocks, has no place for such infinities. It predicts that the core of a black hole is not an infinitely small point, but a region of unimaginably dense yet finite interactions within the causal web. The event horizon, the point of no return, might not be a sharp boundary but a gradual transition, a reconfiguration of the fundamental causal structure itself. This could resolve the infamous black hole information paradox, a deep puzzle about whether information is truly lost forever when something falls in. If space-time is emergent from a network of information processing events, then information might be preserved in the intricate patterns of the underlying system, even as the emergent picture of the black hole evaporates. Perhaps the most tantalizing predictions involve the two greatest mysteries of modern cosmology, dark matter and dark energy. We know they exist because of their overwhelming gravitational effects on galaxies and the accelerating expansion of the universe, but we have no idea what they are. The theory of causal fermion systems offers a radical possibility. It suggests that dark matter and dark energy may not be strange, unknown substances at all. Instead, they could be a signal, a ghost in the machine, revealing the true geometric nature of the emergent space-time. In this view, what we perceive as the mysterious pull of dark matter holding galaxies together could be a subtle distortion in the causal architecture of the universe on vast scales. Similarly, the repulsive force of dark energy driving cosmic acceleration might be a fundamental property of how the causal network evolves and expands over time. It would be like discovering that the strange behavior of a clock is not due to a hidden ghost, but because the gears inside are shaped in a way we never before understood. By providing a completely new geometric picture of reality, this theory reframes our greatest cosmic puzzles not as missing ingredients, but as clues pointing to a deeper structural truth. The universe is whispering its fundamental architecture to us through these mysteries, and we are only just beginning to learn how to listen. These whispers from the cosmos find a remarkable echo in a concept once thought to be a beautiful failure. Decades before the causal fermion system was conceived, the brilliant physicist Paul Dirac wrote down an equation that perfectly described the electron. But his math revealed a bizarre and troubling prediction. It demanded the existence of an infinite, invisible ocean of negative energy electrons, a sea filling all of space. In this picture, what we call a vacuum is not empty, it is this completely full sea. An ordinary electron is just a single ripple floating on top of this vast, unobservable depth. Even stranger, Dirac proposed that if you gave enough energy to this sea, you could knock an electron out of it, leaving behind a hole. This hole would act like a particle with the same mass as an electron, but with a positive charge. He had predicted antimatter, a stunning success. Yet the concept of the Dirac sea itself was deeply problematic. An infinite sea of negative energy was a mathematical and philosophical nightmare, a source of those dreaded infinities that plagued the early development of quantum field theory. It was a powerful but flawed metaphor, eventually set aside for the more abstract machinery of quantum fields. The theory of causal fermion systems does not discard this idea. Instead, it reaches back through time and gives the Dirac sea a new, rigorous and finite life. The entire framework can be seen as a precise mathematical realization of this concept. The underlying causal fermion system, with its vast network of discrete events, is the modern, well-defined version of the Dirac sea. It is no longer an infinite, problematic background, but the dynamic, fundamental structure of reality itself. The vacuum is not a passive, empty container, but the ground state of this system, its most stable and lowest energy configuration. In this picture, particles and antiparticles are not separate entities magically created from nothing. They are excitations, tiny disturbances or defects within this structured sea. An electron is a specific pattern of vibration in the fundamental network. A positron, its antimatter twin, is a different kind of pattern, perhaps a missing link or a twist in the causal web. This solves the old problems of interpretation with breathtaking elegance. There is no longer an infinite, unphysical background because the entire sea is made of a finite number of discrete building blocks. The infinities that plagued quantum field theory calculations simply vanish, replaced by the natural, finite grain of the underlying causal structure. The Dirac sea is no longer a ghost, it is the ocean, and we are the waves. This reframing shows how a powerful but troubled intuition from the past can be resurrected and made whole by a deeper, more complete vision of reality. This starkly different approach sets it apart from the most famous candidate for a theory of everything. String theory has captured the public imagination for decades with its elegant, compelling vision. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, the strings. The properties of each particle, from an electron to a photon, are determined not by what it is, but by how it dances, the specific resonant frequency of its vibration. To make this mathematical symphony work, however, string theory requires a dramatic expansion of the cosmic stage. It demands not just the 3 spatial dimensions we live in, but an additional 6 or 7, all curled up into shapes so small we cannot perceive them. The theory of causal fermion systems walks a fundamentally different path. It is a minimalist dream. Instead of adding new layers to reality, it seeks to peel them back, to reformulate the principles we already know into a more fundamental, discrete structure. It asks a daring question: what if we do not need extra dimensions or vibrating strings to achieve unification? What if the answer lies not in adding complexity, but in discovering a deeper simplicity beneath the equations we already trust? This theory does not replace particles with strings. It reframes what a particle even is within a more primary network, and it stubbornly, elegantly, builds our entire 4-dimensional universe without requiring any hidden, compacted dimensions. The goal is the same, a quantum theory of gravity, but the philosophical starting points could not be more distinct. String theory enriches the stage with new geometry, while causal fermion systems suggests the stage itself is an illusion emerging from a more austere causal logic. One expands the canvas, the other reveals the pixels. Both are monumental endeavors to solve the same profound puzzle, yet they remind us that the ultimate truth might be found through a door we never thought to open. The very elegance of this framework is proven by its ability to clean up the most stubborn mess in modern physics. For nearly a century, physicists performing calculations in quantum field theory have faced a bizarre and frustrating problem. When they try to compute the probability of simple particle interactions, their equations often spit out the answer infinity. This is not a philosophical infinity, but a mathematical one, a result that grows without bound, rendering the calculation useless and nonsensical. Imagine carefully measuring the ingredients for a cake, following the recipe exactly, only to open the oven and find it has exploded into an infinitely large, inedible mess. This is the infinity problem. To get any sensible answers at all, physicists developed a clever but deeply unsatisfying workaround called renormalization. It is a mathematical sleight of hand where you essentially subtract one infinity from another to miraculously get a finite, accurate number that matches experimental results. It works with stunning precision, but it feels like a fudge, an artificial trick that papers over a fundamental flaw in our understanding. We are forced to accept that the universe at its heart is mathematically pathological. The theory of causal fermion systems attacks this problem at its root. Because the fundamental structure is discrete, not continuous, there is a natural smallest possible scale, a fundamental resolution to reality. This simple change in perspective acts like a cosmic regulator. In our calculations, the reason we get infinities is that we assume we can probe infinitely small distances, cramming infinite energy into an infinitely tiny point. But if space-time is a pixelated image, you cannot zoom in beyond a single pixel. There is no such thing as an infinitely small distance, so there is no place for these infinite quantities to hide. The equations of the causal fermion system are written from the start on this discrete canvas, so the answers they provide are always finite, always well-defined. The need for the artificial, infinity-canceling magic of renormalization simply vanishes. The theory does not fix the calculation. It performs a more fundamental one on a stage where the explosion was never possible to begin with. This is not just a technical improvement, it is a conceptual revolution. It suggests that the infinities were never a feature of nature, but an artifact of our flawed assumption of a perfectly smooth, continuous universe. We were trying to describe a digital reality with an analog mathematics, and the causal fermion system finally gives us the correct discrete language. This reinterpretation of the quantum wave function strikes at the heart of a century-old mystery. In standard quantum mechanics, the wave function is the central character, a mathematical expression that encapsulates everything we can know about a particle. It tells us the probability of finding that particle at any given location, but it does not tell us where the particle actually is until we look. This leads to the famous and deeply weird measurement problem. Before observation, the theory says a particle exists in a blurry cloud of potential, a superposition of all possible states. It is only when a measurement is made that this wave function collapses, instantly snapping into a single, definite reality. But what exactly counts as a measurement? Where is the line between the quantum blur and the classical certainty we experience? This has puzzled physicists and philosophers for generations. The theory of causal fermion systems offers a radical way out by demoting the wave function. Here, the wave function is not a fundamental entity. It is not the ultimate description of reality. Instead, it is a secondary, derived quantity, a convenient summary that emerges from the complex, deterministic dance of the underlying causal fermion system. The blurry cloud of probability is not a primary state of being. It is our incomplete view of a much deeper, more structured process. Think of a bustling city seen from a high altitude. You cannot track every single car and pedestrian, but you can describe the city's overall traffic patterns with statistical averages and probabilities. The traffic flow is your wave function. It is a useful description, but it is not the fundamental reality. The fundamental reality is every individual car, every decision made at an intersection, every causal interaction between drivers. The wave function of quantum mechanics is like that traffic flow map. It is an emergent, high-level description of a system that is, at its root, composed of countless discrete causal events. This shift in perspective has profound implications for the measurement problem. The mysterious collapse of the wave function may not be a physical event at all. It could simply be our updating of knowledge as we become entangled with a specific, determinate outcome in the underlying causal network. The universe does not split into parallel realities, and nothing instantaneously collapses. There is just a single, unfolding chain of cause and effect within the fundamental structure, and our act of measurement is merely our entry point into that chain. We are not forcing the universe to choose, we are simply catching up with what has already been determined in the deeper causal fabric of reality. This could finally resolve the paradox of Schrödinger's cat, that poor creature supposedly both alive and dead. In this new view, the cat was never in a superposition. The underlying causal fermion system had already determined the outcome the moment the radioactive atom interacted with the detector. The wave function we used to describe the cat as both alive and dead was always just a reflection of our own ignorance, our lack of access to the full, intricate state of the causal web. When we open the box, we do not collapse anything, we simply learn which path the causality had already taken. This transforms quantum mechanics from a story about chance and observation into a story about a deep, deterministic structure whose complexity appears to us as probability. It suggests that the spooky weirdness of the quantum world is not in the world itself, but in the limited window through which we are viewing it. But a theory that cannot be tested remains a beautiful piece of mathematics, a castle in the air. So how could we possibly prove that reality is built from a causal fermion system? The greatest challenge is one of scale. The grain of this discrete space-time, the size of its fundamental pixels, is thought to be the Planck length, a distance so vanishingly small that it is utterly beyond the reach of any particle collider we could ever build. It would require an accelerator larger than our entire solar system to even come close to probing such energies directly. We cannot see the pixels, so we must look for the artifacts they leave in the picture. We must search for subtle, indirect signatures in the most ancient light and the most precise machines we possess. One of the most promising places to look is the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills every corner of the universe. This radiation is a snapshot of the infant cosmos, and it is incredibly smooth but not perfectly so. It contains tiny, random fluctuations in temperature, the seeds from which all galaxies eventually grew. If the early universe was built on a discrete, foamy foundation of causal fermion systems, that fundamental graininess would have left a specific, subtle imprint on these patterns. It would be like the slight texture of a canvas showing through in a masterpiece painting. As light traveled through the first moments of the universe, the foamy, probabilistic nature of space-time at the Planck scale would have slightly distorted its path, leaving a unique statistical fingerprint in the polarization of this ancient light. Our most powerful space telescopes are already mapping this polarization with incredible precision. While we have not found a definitive signal yet, the theory makes a specific prediction for what to look for, a faint whisper of the universe's pixelated origin encoded in its very first light. Another frontier lies not in the vastness of space, but in the incredible precision of atomic clocks here on Earth. These devices measure time by tracking the vibration of atoms with such astounding accuracy that they would not lose a second in over 15 billion years, the entire age of the universe. In a perfectly smooth, continuous space-time, these atomic vibrations would be perfectly stable. But if space-time has a discrete, foamy structure, then on the very smallest scales, there would be a fundamental uncertainty, a tiny, inherent jitter in the fabric of reality itself. This jitter would cause the ticking of even the most perfect atomic clock to ever so slightly waver over time. It would be like trying to measure a perfectly smooth surface with a ruler that itself has a microscopic, random tremor. These fluctuations would be minuscule, but as our clocks become even more precise, we are entering a regime where we might finally detect this primordial tremor of space-time. Finding such a drift would be a monumental discovery, not just a new particle, but evidence that the very stage of reality is quantized. These experiments and others like them are our only way to listen for the hum of the underlying machinery. We are testing the limits of reality itself, searching for the cracks in the continuum where the true, discrete nature of the universe shines through. This deeper understanding of reality's architecture could unlock technologies that seem like magic to us today. Think about the heart of a quantum computer. Its power comes from qubits, which can be in multiple states at once, but they are also incredibly fragile, easily collapsing from the slightest disturbance from the outside world. If space-time itself is fundamentally discrete, a granular structure built from causal fermion systems, then the very source of this quantum noise might be the continuous, smooth background we mistakenly assume is the default state of the universe. A future quantum computer engineered with a theory of everything might not fight against decoherence. Instead, it could be built to harmonize with the true, discrete grain of reality. Its logic gates would operate in sync with the fundamental pulses of the space-time network, treating the pixelated fabric not as a source of error, but as the native substrate for computation. This could lead to quantum processors of unimaginable stability and scale, machines that do not just calculate, but actually think in the language of the universe's causal structure, solving problems in seconds that would take current supercomputers the lifetime of the cosmos to crack. The potential extends far beyond computing into the realm of our cosmic ambitions. For centuries, our dreams of traveling to the stars have been shackled by the vast, empty distances between them and the hard limit of the speed of light. But if gravity and the geometry of space-time are not fundamental forces, but emergent patterns from a deeper causal web, then the ultimate propulsion system would not be about building a bigger rocket. It would be about learning to reprogram the stage itself. Imagine a spacecraft that does not push against anything. Instead, it uses focused energy to gently reshape the local causal network around it, smoothing out the wrinkles of space-time in front and tightening them behind. This would not be breaking the speed of light within space-time. It would be manipulating the very emergence of space-time to bring destinations closer. It would be like a surfer not just riding a wave, but consciously creating the wave they wish to ride. Such a craft could create a bubble of stable space-time around itself, insulating passengers from the crushing forces of acceleration, effectively making the vast distances of the galaxy negotiable. This is not merely a warp drive from science fiction. It is a logical, if distant, consequence of a theory that treats the fabric of the cosmos as a dynamic, malleable structure rather than a static container. Our journey to the stars may ultimately depend not on conquering space, but on finally understanding its illusory nature. Our minds are wired for a world of 3 dimensions, a tangible reality of length, width, and depth. This makes the mathematical heart of the causal fermion system profoundly difficult to visualize, because it all takes place within an abstract realm known as a Hilbert space. You cannot walk through this space, you cannot touch it. It is not a physical container you could ever build. Instead, think of it as the universe's ultimate, infinite library of possibilities. Every conceivable state of a quantum system, every potential position of a particle, every possible spin, has its own unique address, its own volume in this vast library. The causal fermion system is the librarian, a dynamic network that constantly accesses, organizes, and connects these volumes according to strict causal rules. Now, how does our familiar 4-dimensional world of space and time emerge from such an abstract structure? The key lies in a concept called projection. Imagine a simple 3-dimensional object like a twisting, spiraling piece of sculpture. Now shine a bright light on it and observe its shadow cast on a flat 2-dimensional wall. That shadow is a mere projection, a flattened, simplified representation of the far more complex object creating it. The shadow contains information about the original sculpture, but it is compressed, distorted, and missing entire layers of detail. The true, rich, 3-dimensional form of the sculpture is hidden from the flat world of the shadow. Our 4-dimensional space-time is exactly that shadow. It is a projection, a simplified, low-resolution image cast from the infinitely more complex, high-dimensional reality of the Hilbert space and its causal network. We are creatures of the shadow, and we have mistaken the projection for the object itself. When you see a particle move from one point to another in space, you are not witnessing a fundamental journey. You are observing the shifting patterns in a cosmic shadow play, a consequence of deep, intricate changes happening in the higher dimensional library of possibilities. This is why particles can seem to be in two places at once or tunnel through barriers. From our limited shadow world perspective, these are bizarre paradoxes. But from the higher dimensional view of the causal Fermion system, they are just different pages in the library being connected in a way that our four-dimensional projection cannot fully capture. Our entire reality is a magnificent, coherent shadow, and the theory gives us the first glimpse of the light source casting it. No scientific revolution arrives without fierce debate and unanswered questions. For all its elegant promise, the theory of causal Fermion systems stands at the frontier of physics, facing its own set of profound challenges. The most immediate barrier is its staggering mathematical complexity. The very language of the theory, built upon intricate functional analysis and the geometry of Hilbert spaces, is a formidable fortress that requires years of dedicated study to even approach. This creates a high entry barrier for many physicists, limiting the number of minds that can actively contribute to its development and scrutiny. It is a theory that speaks in a dialect still unfamiliar to the wider community, and translating its profound insights into the more common tongue of quantum field theory remains a monumental, ongoing task. This leads directly to a second major criticism. While the framework beautifully derives the general landscape of quantum physics and gravity, can it recover every single precise detail of the standard model of particle physics? The Standard Model is a masterpiece of predictive power, accounting for every particle we have ever seen in our accelerators with breathtaking accuracy, from the charm quark to the Higgs boson. The true test for any theory of everything is to not just embrace this world, but to reproduce it in all its quirky, specific detail. For causal Fermion systems, this means showing how the specific families of fermions, the exact strengths of the fundamental forces, and the seemingly arbitrary numbers that fill the Standard Model's recipe book naturally emerge from its causal architecture. This work is far from complete. Deriving the full, rich spectrum of known particles and their interactions from first principles is the grand, unfulfilled challenge that stands between it and widespread acceptance. Because of these hurdles, the theory remains a niche pursuit, not yet part of the mainstream conversation in physics. Most research funding and academic focus is still channeled into more established, though equally troubled, avenues like string theory or loop quantum gravity. This is not necessarily a dismissal of its potential, but a reflection of the conservative nature of scientific progress. A paradigm shift requires not just a brilliant new idea, but a gradual accumulation of results, predictions, and a community of researchers who can build upon it. The theory of causal Fermion systems is still in its adolescence, building its mathematical muscles and searching for that one decisive prediction that could force the entire world to take notice. Its greatest strength, its foundational purity, is also its greatest burden. It asks us to abandon our most comfortable intuitions about space and time before it can fully show us the new world it promises. The path forward is clear yet steep. It must mature from a compelling framework into a precise engine of prediction, bridging the gap between its profound abstract beauty and the tangible, particulate world we know exists. The path from a beautiful mathematical framework to a tested physical theory is a marathon, not a sprint, and for causal Fermion systems, that race is actively underway in research centers across the globe. A small but dedicated community of physicists and mathematicians are now translating the abstract elegance of the theory into concrete, computable models. At the forefront of this effort are pioneers like Felix Finster and his collaborators, who are meticulously building the bridges between this new foundation and the familiar world described by the Standard Model. Their work is painstaking, often comparing the process to learning a new language while simultaneously trying to rewrite an entire library of existing knowledge. The equations of causal Fermion systems are profoundly different from those of quantum field theory, and extracting their specific predictions requires a deep and patient form of mathematical archaeology. This is not about inventing new particles on a whim, but about carefully excavating the known particles from within the theory's intricate causal architecture, proving that everything we see is naturally housed within this new structure. To aid in this monumental task, scientists are turning to some of the most powerful tools in modern science, supercomputers. The equations are so complex that they often defy traditional pencil and paper analysis. Researchers are now writing sophisticated code to create numerical simulations of causal Fermion systems, building simplified model universes inside a machine to watch them evolve. They set the fundamental rules based on the theory's principles, let the simulation run, and then observe what emerges. Do the familiar patterns of four-dimensional space-time crystallize from the digital chaos? Do collective excitations appear that behave just like electrons and quarks? These simulations are virtual laboratories, allowing physicists to explore the consequences of the theory in a controlled environment, searching for those crucial signatures that could one day be matched against real-world observations. This computational approach is vital for stress testing the theory's internal consistency and for generating those testable predictions about cosmic microwave background fluctuations or the jitter of atomic clocks. Every line of code, every simulation that successfully recovers a piece of our known reality, is a small but significant step forward. It is a slow, deliberate process of building confidence, brick by mathematical brick, in the hope that this radical new picture of reality might just be the one we have been searching for all along. This relentless causal ordering might finally answer a question that has haunted physics for over a century. Why does time have an arrow? In our daily lives, the forward march of time is undeniable. An egg cracks and scrambles in a pan, but the scattered pieces never leap from the plate to reassemble into a whole shell. We remember the past, but not the future. The universe seems to possess a built-in direction, a clear distinction between what was and what will be. Yet, the fundamental laws of physics, from Newton to Einstein to quantum mechanics, are almost entirely time-symmetric. The equations work just as well if time runs backward. So where does this overwhelming sense of direction come from? The theory of causal Fermion systems suggests the answer is woven into the very fabric of its architecture. Remember that the entire structure is defined by a web of strict cause and effect relations. This network is not static, it is dynamic and evolving. With each new fundamental event, the entire configuration of the system updates, but it can only update in one direction, following the unbreakable causal chain. You can think of it like a cosmic game of dominoes, where each tile represents a fundamental fermionic event. Once a domino falls, it can only knock over the dominoes in front of it, those in its causal future. The chain reaction is irreversible. The system cannot spontaneously reassemble itself into a prior configuration because that would violate the causal order that defines it. The arrow of time, in this view, is not an added ingredient, but the direct manifestation of this irreversible progression through the network's possible states. This progression is deeply tied to the very nature of the fermions themselves. Recall their stubborn individuality, the Pauli exclusion principle that prevents them from occupying the same state. As the causal Fermion system evolves, the number of possible configurations for its fermions increases dramatically. The system explores new, more complex arrangements, and it cannot easily go back to simpler ones. It is like shuffling a deck of cards. There is only one way for the deck to be perfectly ordered by suit and number, but there are an astronomically vast number of ways for it to be disordered. Once you shuffle the deck, the probability of it randomly returning to that single, perfect order is vanishingly small. The universe in this picture started in a relatively simple, low-entropy state, much like that ordered deck. As the causal network evolved, the fermionic configurations became exponentially more complex and numerous, just like a thoroughly shuffled deck. The arrow of time is the feeling of this cosmic shuffling, the inevitable journey from simple order to complex disorder, driven by the causal connections between fermions that cannot backtrack. Our experience of time flowing forward is our perception of the universe relentlessly exploring new and more intricate states within its causal web, a journey that, by its fundamental design, only moves in one direction. This granular architecture of reality might even hold the key to our own inner universe. If space, time, and matter are all emergent phenomena from a deeper causal network, then what are we? Our thoughts, our feelings, the very light of consciousness itself, must also be rooted in this physical substrate. The human brain is, after all, a vast collection of fermions, electrons, and quarks organized into neurons with trillions of intricate connections. Could the mind be more than just the chemical soup in our skulls? Could it be a specific, incredibly complex pattern of excitation within the universal fermionic network? In this view, your conscious experience is not a ghost in the machine, but the machine itself, operating at its highest level of organization. When you have a thought, you are not creating something separate from the physical world. You are initiating a specific, cascading pattern of causal interactions within the fundamental structure that is your brain, a pattern that is so intricate it gives rise to self-awareness. This is a profound shift from the old idea of a soul separate from the body. It suggests that consciousness is not a substance but a process, a dynamic dance within the causal web. Think of a whirlpool in a flowing river. The whirlpool has a distinct identity, a stable form that persists over time, yet it is made of nothing but the water itself, constantly flowing through. You can point to it, describe its behavior, but you cannot grab a handful of whirlpool. It is a pattern, not a separate thing. Consciousness could be like that whirlpool, a persistent, self-sustaining pattern in the flow of the fundamental fermionic sea. This perspective dissolves the hard line between the mind and the physical world, because they are both manifestations of the same underlying reality. Your thoughts are as physical as a star, just expressed through a different, more complex arrangement of the cosmic code. What does this mean for the nature of reality itself? If our minds are patterns within this network, then the reality we perceive is not a direct recording of the outside world. It is a user interface, a highly processed simulation constructed by our brains to help us navigate the overwhelming complexity of the fundamental causal web. We do not see the raw data of the Hilbert space. We see a useful model built from it, complete with colors, sounds, and the solidity of objects. This model is so effective that we mistake it for reality itself. But the theory suggests that the true nature of existence is this vast, interconnected network of discrete events, and our conscious experience is a brilliant, simplified rendering of that deeper truth. This raises a staggering possibility. If consciousness is an emergent pattern, could it exist in other substrates? Could a sufficiently complex arrangement of any part of this causal network, not just a biological brain, give rise to awareness? It hints that mind might not be a rare accident of biology, but a fundamental potential of a structured universe, a natural consequence of complexity arising within the causal Fermion system. We are not just observers of the cosmos, we are the cosmos becoming aware of itself, a fleeting but magnificent pattern in the eternal sea of causality. This radical rethinking of the universe's fundamental nature demands an equally new story of its birth. The traditional Big Bang narrative begins with a singularity, a moment of infinite density and temperature where our current laws of physics simply fail. The theory of causal fermion systems offers a different genesis, one without a starting singularity. In this picture, the early universe was not a hot, dense point. Instead, it was a specific, highly organized configuration of the underlying causal fermion system, a state of profound symmetry and simplicity. Think of it not as an explosion from a single location, but as the entire network of reality initializing in its most basic, orderly state. This pristine configuration would have been like a perfectly still, crystalline lattice, a starting condition defined by the mathematics of the system itself rather than a violent, unknowable beginning. From this elegant starting point, the universe did not bang into existence, it began to compute itself. The inherent dynamics of the causal fermion system, governed by its strict causal rules, would have naturally driven this symmetric state to evolve to become more complex. This evolution is the true origin of our cosmic timeline. The initial symmetry began to break, and as it did, the first structures of emergent space and time began to flicker into being. This process of symmetry breaking is like a vast cosmic game of dominoes being set in motion. That first perfect row of dominoes represents the symmetric early universe. It is stable, but it contains immense potential energy. The slightest nudge, an inherent fluctuation in the system, tips the first domino. A wave of change then ripples through the entire network, a cascade of causal links forming and breaking. With each falling domino, with each update in the fermionic configuration, the system moves from a state of high order to one of increasing complexity. This cascade is the birth of time, and the expanding web of new causal connections is the birth of space itself. What we call the Big Bang in this view is not the beginning of the universe, but the moment this transformative evolution became rapid and dramatic, the moment the dominoes began to fall in earnest, creating the expanding, cooling arena we now inhabit. This narrative elegantly sidesteps the problem of the initial singularity. There is no point of infinite density because the universe was never a single point. It was always a structured, albeit simple, network. The question of what came before the Big Bang also transforms. There was no before in terms of time, because time itself emerged from the evolution of this network. There was only the initial state, and then the first causal step that set everything in motion. This framework also provides a potential alternative to cosmic inflation, the popular theory that the universe underwent a fantastically rapid expansion in its first moments. In the causal fermion picture, the smooth, large-scale universe we see today might not be the result of a brief period of hyper-expansion, but a direct consequence of the initial symmetry and the specific way the causal network unfolded. The uniformity of the cosmic microwave background could be a frozen echo of that pristine initial state, a relic of the universe's original, highly ordered configuration. This is a new kind of cosmology, one where the history of the cosmos is not written in the language of fields and particles within a pre-existing space-time, but is instead the story of a dynamic causal network discovering its own geometry, moment by moment, from a state of perfect simplicity to the rich, complex universe we call home. Physics textbooks would begin not with a falling apple, but with a question. The very first chapter would ask students to forget everything they think they know about the stage of the universe. Instead of launching directly into Newton's laws of motion, the curriculum would introduce the concept of emergent reality. Students would learn that space and time are not fundamental backdrops but collective behaviors, much like the concept of temperature arises from the motion of molecules. This foundational shift would reframe the entire purpose of physics, presenting it not as the study of objects moving in a container, but as the study of how the container itself is built from more basic causal ingredients. The familiar formulas for force and acceleration would still be taught, of course, but they would be presented as incredibly accurate approximations, effective rules that work perfectly within our emergent, large-scale reality. The mystery would no longer be why the apple falls, but why the stage exists for it to fall through at all. This new narrative would transform students from passive learners of established laws into active investigators of reality's deepest architecture. Imagine a high school lab where students run computer simulations of simple causal networks, watching as concepts like distance and before and after crystallize on their screens from a sea of abstract points. They would not just be memorizing equations, they would be witnessing the genesis of physics itself. This educational revolution would cultivate a different kind of scientist, one who is inherently comfortable with the idea that our most basic intuitions about the world are approximations, opening minds to a universe that is far stranger and more wonderful than a simple, continuous stage. The goal would no longer be to fill a vessel with known facts, but to ignite a spark of fundamental inquiry, empowering the next generation to ask the questions we have not yet even thought to form. For a theory this profound to move from the fringe to the foundation, it must first learn to speak the language of proof. The journey to mainstream acceptance is a gauntlet every revolutionary idea must run, and for Causal Fermion Systems the path is paved with three distinct challenges. The first and most critical is the demand for concrete, testable predictions. While the theory beautifully reframes our cosmic puzzles, it must now move beyond elegant reinterpretations and tell us something new. It needs to pinpoint a specific energy signature, a precise distortion in starlight, or a measurable jitter in a quantum system that no other theory can account for. This is the currency of physics, a hard prediction that can be taken into a laboratory or pointed at the sky for verification. Without it, the theory remains a magnificent philosophical sculpture, admired but not yet part of the working engine of science. The community is waiting for that one bold, numerical forecast that can be written on a whiteboard and tested, a prediction so clear it forces every physicist to pay attention. Yet, making such precise forecasts is hampered by the theory's second great hurdle, its daunting mathematical complexity. The very language of Hilbert spaces and functional analysis, while powerful, acts as a formidable barrier to entry. It is as if the theory is written in a dense, ancient script that only a handful of dedicated scholars have taken the years to learn. For it to attract the vibrant, collaborative community it needs to thrive, this language must be translated. Researchers must find ways to simplify its presentation, to extract its core physical insights and express them in the more familiar dialects of quantum field theory and general relativity. This is not about dumbing down the ideas, but about building bridges. It requires creating new textbooks, graduate courses, and accessible review papers that allow a bright young physicist, curious but not yet an expert, to grasp the central concepts and start contributing. The theory needs its own ambassadors, those who can act as interpreters between its abstract beauty and the practical, hands-on world of experimental physics. Ultimately, the final step on this path is the discovery of a smoking gun. Every accepted theory in physics has one, a single experimental result that simply cannot be explained by the old way of thinking. For general relativity, it was the bending of starlight by the sun during a solar eclipse. For the Standard Model, it was the discovery of the Higgs boson. Causal Fermion Systems needs its own moment of undeniable validation. This could be the direct detection of space-time foam in the light from a distant quasar, a specific pattern of drift in a network of atomic clocks that defies all other explanations, or a calculation of a particle's mass that emerges perfectly from first principles. That one result would be the tipping point, the evidence so compelling that it would shift the entire conversation. It would force the mainstream to stop viewing the theory as a curious alternative and start seeing it as the most viable map to a deeper reality. The quest for this definitive signature is what drives the small but determined community working on this idea today, a quiet search for the crack in reality that proves the stage was always an illusion. Our journey began with a crisis, a fundamental crack in our understanding of the cosmos where two magnificent theories could not be reconciled. From that fracture emerged a breathtakingly bold vision, the theory of Causal Fermion Systems, which dares to rewrite the cosmic rulebook from the ground up. This is not just another attempt to patch the old framework. It is a proposal for a new foundation, one where the very distinctions we take for granted between matter and the space-time it inhabits simply dissolve. In this picture, reality is not built on a smooth, continuous stage. It emerges from a dynamic, discrete network of causal events, a cosmic computation where the actors and the stage are born from the same fundamental script. This perspective has the power to revolutionize everything. It reframes gravity not as a force, but as the natural geometry of an emergent fabric. It dissolves the baffling paradoxes of quantum theory by suggesting the wave function is merely a shadow of a deeper, deterministic dance. It offers a genesis for the universe without a singular, infinite beginning, and it provides a natural, finite answer to the infinities that have plagued physics for a century. The potential is staggering, pointing toward a future where technologies we consider magic, from stable quantum computers to cosmic propulsion, become conceivable by harmonizing with the true, granular nature of reality. This entire edifice rests upon the unique character of the Fermion, the ultimate individualist of the particle world. It is a profound thought that the deepest secrets of the cosmos, the origin of time, the fabric of space, and the nature of consciousness itself, might all be encoded in the stubborn, structured behavior of these fundamental entities. The research continues, a quiet revolution unfolding in papers and simulations across the globe. The greatest discoveries in physics have always come from questioning our most basic assumptions. So stay curious, follow this ongoing quest, and the next time you look up at the seamless night sky, ponder the incredible possibility that you are witnessing a magnificent illusion, a masterpiece painted with the discrete, causal strokes of a cosmic fermionic system.